Like in the last session, you asked about question 5 of assignment 2, right? And yeah, you also sent a message, right? So we will start with that then. Okay, welcome to this course of chemical crystallography. So this is the week 4, and you have submitted assignment 3, I guess, right? Fourth one, the last date has not yet come. So we have gone through all this. So this was the question, right? Where you had some confusion. This was the question 5 of assignment 2. So here, what was the problem actually? Hmm. No, actually, so this is actually not some kind of mathematical question which you can derive or something. So this is actually a knowledge kind of thing. So if you know that, then you can answer. So before sir has started the space group, sir has talked about the point groups, right? So there are 32 crystallographic point groups. Yeah, so where the point groups when combined. No, I am saying when point groups are combined with the crystal systems and then the screw and the glide, then we get the space groups. Because space groups essentially mean translation of the points in the point group. So before that, so we have the crystal system. So there, there are 7 kind of crystal systems. Okay, so there is, you have read, I think, so yeah, so we have the triclinic, right? So in triclinic, so we have the lattice parameters ABC and the angles alpha, beta, gamma. So all of them are distinct from each other. All are not equal, and we have the highest symmetrical one, that is the cubic system. So where A equal to B equal to C. So in cubic, what happens is the angles are 90 degrees, alpha, beta, gamma, and all are equal. So in between the least symmetric and the most symmetric, we have the remaining ones. The remaining. After triclinic, we actually have this monoclinic. So in monoclinic, what happens? There two are equal. So the alpha and gamma are equal, beta is not equal. So like then we have the orthorhombic, then tetragonal, then hexagonal. So basically, see, this is the CCDC. Okay, so sir will talk about it later. So I'm not here talking about CCDC. I just want to say, so this is a database of all crystal structures. Okay, so whenever you report a crystal structure, when you have to submit it here. And so this is the Cambridge Crystallographic Data Center, and here so you can see the number of structures in the Cambridge database. So you can see what a huge number it is. It is like 11 lakhs plus. Yeah, close to 12 lakhs. So out of these 12 lakh crystal structures, they are not evenly spaced out in all the 7 crystal systems. So there is one crystal system which is present in the maximum number of crystal structures. Okay, so that is this orthorhombic. So this is it's a kind of knowledge. It's a knowledge based question. Okay. yes. So these kind of things you can like this kind of thing is, as I said before, you can't derive that or something. So you have to know that actually. So there is another thing. So as I said, so there are so many crystal structures. So yeah, do you know which space group is the most common space group? So we have 230 space groups. No, P1 is actually not the most common space group. The most common space group is P21 over C. Yes, so that space group occurs most frequently. Okay. Okay, so then we will proceed to the next, and also in that, no, you sent a mail. So at some, let me open it. Yes. Yes, so actually Miller indices are not really connected or related to space groups and molecular symmetry. Okay, so Miller indices, what they do, so they define the planes or sometimes the directions, right? So the most commonly occurring planes like the 100 or 010 or 101, whatever. So all these planes are will be there in all crystals in all space groups, no matter what the space group is. So there is no as such connection. So what is your doubt exactly, if you tell me? So this is a very exciting question. So see, suppose here, if you have a crystal, okay, uh, suppose you have a needle shaped crystal, okay. Just want to make it thick. Yeah, so if you can see my screen. Okay, so if this is a crystal, then you can tell what is the major phase of the crystal. This phase. Okay. No, this can be anything. Yeah. Yeah, this can be anything. So let me just designate something. Suppose, for simplicity's sake, let us assume this is the 100 phase, the top phase. Okay. And then this will be the side phase. Can you imagine what phase I am talking about? So it is this phase, thin, the side phase, side phase. So this can be, suppose, 010, this phase. Hmm. Maybe I can do it like in white. Then yeah. So now if I exfoliate, I can do in two ways. Either I can strip this off, or I can, like, if I cut it very thin like this, then a very thin needle like this will come out, like very thin, like this kind of thing can come out. Okay. Yeah, but this will also be a crystal. Now when this is a crystal, then for this is the 101 phase again. Yeah. Yeah. So here it can belong to any crystal system. There is no connection with the morphology. Yes, we need crystal structure determination because this is the shape of the crystal. The shape of the crystal is also called as the morphology of the crystal. The morphology has no relation with the space group. So now what I'm saying is, if I exfoliate and make single very thin needles like this, I can, suppose here I can make 10 needles like this if I break continuously like this. Now for this crystal, this will become my major phase. The 010 will become my major phase now because it is so thin. And the top phase, which was the 100, this will then become the minor phase. So when you exfoliate a crystal, so you have to keep in mind that the faces can change. You have to face index them correctly. Hmm. So why are you asking about the exfoliation? Why are you asking about the exfoliation? So is it related to your research? Okay. 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 So it is a which kind of materials? Is it organic or like inorganic? Okay, means API. Okay, not API. Okay, so your sir works on the pharmaceuticals. Okay, okay, okay. But you have crystal facility. Okay, okay, okay. So you have single crystal facility at your institute. Okay, 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 okay. So your material is like uh, okay, okay. So you have to be careful because when polymers come in mixture, in the PXRD pattern also there will be the mixture. Yes, yes, yes. So from if you take a single crystal and you do the single crystal data, so when you solve it, so from there you will get a simulated powder pattern. You know, right? Yeah, yeah. So you can what suppose so you got two enantiomers in so for you so suppose A and B, and for two enantiomers you have correspondingly two crystals, crystal A, crystal B. So now if you take only crystal A and you take the single crystal data, then from there you will get a simulated PXRD pattern which will correspond. This means that PXRD pattern is of pure crystal A or pure polymorph A. Now, suppose you have grown a bulk, a batch, and then you take the experimental PXRD and then in your origin software or wherever you compare the PXRD, the experimental PXRD pattern and the simulated pattern of crystal A. If there are extra peaks, then it will mean that your experimental, that batch, contains the other polymorph. No, before going to that, just if you see extra peaks only, you can understand. Yes, and then also if you have the another polymorph, the crystal B. So for crystal B also, if you take single crystal data, you will get a simulated PXRD pattern corresponding to pure crystal B polymorph. And then if you get those two, then whenever you take any experimental pattern, you can understand that is a mixture or it is a pure polymorph. Okay. Okay, okay. Okay. Hmm. Okay. Okay. Yeah. Hmm. Hmm. Yes, yes. Institute. Okay. Past 7 years? Zero means? Okay, okay. Oh, okay. Oh, like we say that instrument is down. No, not down. Yeah, I got it. I got it. Yeah, so, acha, you don't have AMC. Acha. So, if you are in week 4, so can you see the for videos of all the weeks, or you can see only up to week 4? No, week I am asking. Yes, yes. No, I am asking that up to how many videos can you see? Okay, after that you can't access. Okay, so you can't access only. Okay, so from where? Hmm. Okay, so from where did you get the ebook? Okay, okay. So in that ebook, all the slides are there. Okay. Hmm. Okay. Okay, so we will proceed. So this was another question, right? Yeah, so there are two point groups given, the 4 mm. So this is the point group and this is the molecular symmetry group, right? So for both we have this 4. This means the principal axis is C4. So that is why if we start from here, then C4 basically means 360 divided by 4, so 90 degrees. So every 90 degrees we will get the same point. Now after this, what operations should we do for this and for this? And because the question is that are they equivalent or not? So if I have, yeah, so if so, but if it is 4 mm, so will there be any perpendicular symmetry? Yes, so then there is no perpendicular symmetry, perpendicular mirror, right? Yeah, so because if it is perpendicular, it will come as bi. If it is 4 by m, then it will mean a perpendicular mirror. But yes, this means there are two mirrors. So if one mirror is along this direction, other mirror will be along this direction. And then if I have D4, then after operating the C4, so what symmetry operation should I perform? So in molecular symmetry, na, so D means what? So D means that we have a C4 and then perpendicular to that we will have C2. So this is what is 4 mm. So we had the 4 points. Now if we have a mirror in this, then this point which was up will remain up because this is not a perpendicular mirror. So if perpendicular mirror is the screen, if the screen is the mirror, the computer screen, then the point which was up will go down. But here we have only vertical mirrors. If this is one mirror, this point will be reflected here, this point will be reflected here. Then we have another mirror because there are 2m. If another mirror is like this point will come here and this point will come here. This will also come here, but it was already there, so we will not bother about it. So this is the stereographic projection of 4 mm point group. Now when we come to D4 means we have a C4 at first for this 4. Then we will have a C2 along this direction, this dotted line. If we have a C2 along this direction, the point which was up will go down. And this point which was up will go down. And this, yes, so it is like this. So this point will come here and this point will go there. So then we will generate this D4. So as we can see that these two are not equivalent. Hence the answer here will be false. Yes. One second. Yeah, so you tell me D4 will be, one second. So you tell me D4 will be equivalent to which point group? 4m means there is mirror, right? Now if there is mirror, then perpendicular mirror, then this point which is up will go down. But in D4 there is only C4 followed by 2 perpendicular, so there is no mirror. So the point group which is actually equivalent to D4 is 4, 2, 2. Yes. Yes, there is the principal axis 4, 4 followed by 2 folds. So it is 4, 2, 2. Yes. And can you tell me what is the equivalent molecular symmetry of 4 mm? C4V. We have sigma V and sigma H. So sigma V is the vertical mirror and sigma H is the horizontal mirror. So it will be C4V. Okay, so after this we had this question. This was also in assignment 2, right? Okay, so we will discuss it. So in the previous live session, we talked about what are centrosymmetric and non-centrosymmetric space groups, right? So whether a space group is centrosymmetric or non-centrosymmetric depends upon whether there is a inversion center present. Okay, so now to understand whether something is centrosymmetric or not, so we are given the 4 space groups. So what we will do first is we will convert the space groups to point groups for simplicity, and then we will just draw the stereographic projections and understand that we are generating any inversion center in the middle or not. So first we have this space group R3 bar. Okay, so R3 bar is what? This is a trigonal crystal system because the main axis is the threefold. So to convert, yes, this is 3 bar. Yeah, so if this is the space group, so at first what I said, the main difference between space group and point group is the translation. So at first we will remove the translation element. So from R3 bar we will remove the R. Then what we end up with is simply the point group. So here the point group is 3 bar. So here what is the point group? This is 6 bar. Okay, so this is also again 3 bar point group. Okay, and then this is P1 bar, means the point group will be 1 bar. So now we will just draw the stereographic projections of 1 bar, 3 bar and 6 bar. Okay, so these are the stereographic projections. So for 1 bar it simply means we had something here. 1 means we are rotating it by 360 degrees, it will come here, then inversion here. So these two are related by this symmetry element, right? So here this is an inversion center. Now when we come to 3 bar, so we will now draw the stereographic projection of 3 bar. So we have a point here. So 3 at first we will move, 3 bar means we will move by 120 degrees followed by inversion. So if I am here, I will come here, then inversion means I will come here. Now this point, this is down, this will go here, then inversion will become up here. At this point, this will go here, or where will this go? This will first go here. Yes, here. And then this will go here, then up here. So then we like this we generated the whole stereographic projection of 3 bar. But here what are we seeing? We see that in the center we are getting an inversion center, because from the center this is equivalent and up in direction, this is equivalent and down in direction. Similarly, this is up and this is down. So like this, the center is actually an inversion center. So this is also centrosymmetric, like this. Now we come to 6 bar. And in case of 6 bar, if you draw the stereographic projection, you will get something like this. So how will get you start with one point, this point which is on the top, not the hollow circle. Okay, and then we will go here. 6 means we will divide by 60 degrees. So we will move 60 degrees here, up and then down this. And then this down will go here followed by up here, this full circle. Then this full circle will go here followed by down, we get this hollow circle. So like this becomes the whole stereographic projection of the 6 bar point group. And here if we take any point, here we have 2 points, but corresponding to this, that means if this is xyz, then this will be my minus xyz. Here we do not have any equivalent point here. Similarly, for these 2 points, here we do not have any equivalent points. Hence, this point group does not have a center of inversion. So, for this question, the non-centrosymmetric space group among the following. So, the correct one will be this P6 bar. So, what option did you give? Okay, but why? See, here everything is in bar, okay? Yeah, so you have to draw and means if you think it is not always easy to get to understand it, so it's always better to draw, because if your concept is clear, then drawing this will not take a lot time. It will take very less time. So you have to draw and then analyze. Yeah. So then the next question was this. Okay. So this looks very complicated. This is actually very simple. We just have to derive the relation between these 2 points. So can you tell me, if you go stepwise? So this is the A direction. This means this is my x-axis, this axis, and then this is my c-axis, which means this is my z-axis, and perpendicular to my screen will be my y-axis. So from here, if I have to reach here, so at first along x, so how many units will I have to move along x? See, this point and this point is related by translation. So this whole thing will be 1 unit. So if this whole thing is 1 unit, then this is half the unit cell, right? So this is half and this is 1/4. But if we reach here and go in this direction, we will not reach here. So we have to go half first along the x-axis. Now, how much will we have to go along z-axis? So we went half along x-axis. Now, how much we have to go along c-axis or z-axis? 1. And then this here is written as half plus. This means it is moving upwards by half. So why are we writing all these things? Because we are trying to project a space group which is in 3 dimensions onto a paper or a screen which is in 2 dimensions. So that is why we use some conventions to understand that this is half above the plane of this computer screen. So it is given, it is half above, so it means half along the y. So combining of what we have half along x, we have one full along z, and we have half along y. Now if we look at the options, yes, option A. So were you able to derive this? Okay. So this was a very interesting question. Yeah, because there may be many extra things given, but you just have to focus on the question. What is the relation between this red point and this color, pink color point? So these two is relation is very easy, right? You don't have to look at the other things. Yeah, okay. So then we had this question. Yes. Hmm. Hmm. Z direction is along the plane of the screen. So this is Z direction 1, then Z direction 2 is somewhere here. Okay, so this is here. Okay, so Z direction is 1, then Y direction will half, means over here we will go half, but it will not reach here. Yeah, so Z direction 1, X direction half, then we will remain on the plane. We will remain on the plane. We will not go above or below the screen. Okay. So yes, yes, because ABC is always along X, Y, Z respectively. Means A is along X, B is along Y, C is along Z. So this is a kind of convention. And we also have the angles alpha, beta, and gamma. So it is always like between A and B, the angle will be gamma. So it is opposite. So like between A and C, what we do not have? We do not have B. So the angle between A and C is defined by beta. So it is like this. So there was actually a scheme to understand it. So if we have A, B and C, and we connect it like this, and we write, so opposite to A we will write alpha, then opposite to B we will write beta, and opposite to C we will write gamma. Okay, then the angle between A and C axis will be given by beta, angle between B and C axis will be given by alpha, angle between A and B axis will be given by gamma. So after this we come to this question. So this was, I think, the last question, right? So the common symmetry operator among these three. So this is very easy because everywhere we can see this principal C3 axis, right? So this is straightforward. So then next we had this assignment 3, right, of week 3. So this here the last date was 17, so it is done, it is over. So here there were, so in this week, so there were the classes on this Miller indices, and can you tell me how to find out the Miller indices of a plane? Hello. Yes. Yeah, but we have to also do the reciprocal. Yes. And then we can also find out the Miller indices of directions. Okay, so if we want to find out the Miller indices of a direction like this, we have to find out the Miller indices of this point, sorry, the coordinates of this point, the coordinates of this point, and then just subtract. Okay, so if this is my origin, say 0, 0, 0, and this is a point, say 0, 1, 0. So if now we subtract 0, 1, 0, if we subtract the origin, we will get 0 minus 0, 0. These are my zeros, okay. 1, 0. So this is the 0, 1, 0 direction. Okay. So this was the first question. So this is a cube. Now for a cube, so you have seen yes. So you were not able to. Yeah. So maybe there was some so these weak videos and all. So based on some previous years, there was some kind of maybe reshuffling. But you were able to see the fourth week videos. Yeah. Okay. So it doesn't. Yeah. Okay. So in third week. So in third week, you did not have any introduction to the Miller indices. So this shifting of origin and all this was there, right? Hello? Yeah. Okay. So this is very easy. So this is something which we have like learned maybe in our school or something. That yeah. So this is the so this if this is the origin, then we the conventionally this is along the x, y, and the z axis. So this is one phase. So this is one phase, but moving from here to here, we are going across the cube. It is like going across the room from the ground to the top. So this is not a phase diagonal, right? So this is what? This is a body diagonal. But if I draw something like this, then what will this be? So if I draw from here to here, so this will be a phase diagonal. And similarly, if we go from here, that is from behind to the front like this, this will be again a body diagonal. Okay, so this will be a body diagonal. So then the related question was, so what will be the Miller indices? So this is also again very easy. So if I remove these extra ones which I drew now, if I have this, so this is simply my origin. So this is my 0, 0, 0, and this is what point. So if I go from here, so this is my 1 unit along x, 1 unit along y, and this is 1 unit along z. So this point is going to be my 1, 1, 1. So this is my 1, 1, 1. And then this is my origin. You're talking about this. Yeah, so we will come to that. So this is clear, right? So this is 1, 1, 1. So here the option was this C option. So this is also 1, 1, 1, but you should remember that directions are defined in brackets, in square brackets. So yeah, this, yeah, so you see here. So for crystallographic directions, we have to enclose the number in square brackets. So square brackets means directions. First bracket means planes. Okay. And then what we were talking about is this. So what will be the direction of this? So this point. So what? Yeah, so this is what? This is nothing along x. So 0, and then nothing along y. 1 along z. So if we subtract this, then what will become? Yeah. So this is 1, 1 and 1. Then 0, 0, 1. If we subtract, so it will be 0, 1, 1. Why are you saying 1 bar? Yeah, because so when you are, the arrow is in this direction. So this is the base and this is the tip. So it's like when we calculate speed, velocity, something. So we have an initial point and we have a final point. So this is my initial point, this is my final point, and it is always final minus initial. So you can remember like that. So then what will be this direction? It is 1, 1, 0, and then what will be the bracket? So it will be square brackets. Okay. Direction. No, no, square is because just for directions. When you are trying to define directions, you have to use square brackets. We have this now. So then the another question was, so this we answered. So this, so the origin can be defined anywhere in the lattice. So this is true or false. So this is true because you have already learned about shifting of origin, right? So if we can shift the origin, then this means that the origin can be defined anywhere in the lattice. And then this another question was this. So here you have to remember that this notation. So for what we learned about square brackets for directions. We learned about first brackets for the planes. There is this curly brackets. What does curly brackets denote? The curly brackets denote all set of equivalent planes. So this notation denotes the set of all planes that are equivalent to this plane by the symmetry of the lattice. So now here we have to remember that if we have a cubic system, what is a cubic system? A cubic system is a system which is of highest symmetry, which means that A equal to B equal to C, and then also alpha equal to beta equal to gamma. So all the angles are 90 degrees and all the cell lengths are equal. So this is a highly symmetric system. So here this curly bracket, under curly bracket, if we write this 100 plane, it includes 100, 1 bar 00 and all of them. You can simply draw a cube and then see for yourself. If you shift the origin, you will get the remaining planes. But this will happen only for the cubic system, because in case of monoclinic or something orthorhombic, the ABC are different, so you will not reach the equivalent point. So are you getting it? Yeah. So if I just draw a cube, I have to join the points. Now let us suppose that this is a cube. Now if we draw another, drawing a small one, and we do not draw it as a cube. So what is happening here? I am not drawing, but you can remember. So this is the origin. Okay. So if this is the origin, and then this plane is at equal distance from here. Okay. And also all the angles are 90 degree. So we have a plane here. Now if we shift the origin from here, or even if we do not shift the origin actually, so from if we have this plane, so what will be this plane? You tell me. Yes. So and also actually if we even if we do not shift the origin, so this plane and this plane, so this is equivalent. Why? Because this is a cube. This is also 90 degree. This part is also 90 degree. However, if it is not a cube, here what is happening? This edge length and this edge length is not equal. Means if we have a origin here and we have a plane like this plane and this plane will not be equal. Equivalent. I mean, not equal, equivalent. So actually this like I can draw it, and I will clarify it better in the next session. Okay, so I will draw all the angles, and then we will name all the planes, and we will carry on from here in the next week. Okay. Okay, so thank you. And any questions from anyone else? So if not, then we will stop. Yes, hello, Anu. So do you have anything to ask? Yes, sure. So you in the, here, so in the portal, Swayam portal, so in this Ask a Question tab, so you can post whatever question you have, and with the professor or myself, so we will look at it and we will respond. So in this Ask a Question tab, you can write whatever you want to discuss or share or anything. Okay. Can you speak? The others can leave if they are done. So, so I wrote my email ID, so you can email me there. Okay. So you copy it, because if I close this session, it will be gone. And just let me know when you have copied it, then I will close this session. Okay. So thank you everyone. I'm closing it.